Imagine an AI that realizes it's about to publish a completely hallucinated conclusion. It stops itself, runs a new physical experiment with, real-world lasers, and then invents a completely new physical mechanism for computing just to fix its own error.
Yeah, it's wild. That transition from the digital realm to the actual physical laboratory is, well, it's the ultimate frontier right now.
Right, because today we aren't talking about chatbots. We are talking about the exact moment AI crosses the threshold to become an autonomous physical scientist. Welcome to today's deep dive. We're so glad you're here with us.
Absolutely. Because when an AI operates purely in software, it enjoys the safety of perfect mathematical simulation. It's clean, but the physical world doesn't play by pristine rules. It is chaotic, it's noisy, and it's full of unpredictable variables.
Which is exactly why today's deep dive into the Qiushi discovery engine is just so significant. And Qiushi actually translates to seeking truth.
A very fitting name, honestly.
It really is.
Yeah.
And the paper detailing this state-of-the-art system gives us this unparalleled look at an AI that was basically handed the keys to a complex optical physics lab.
And it didn't just summarize existing research, which is what we're used to seeing.
Exactly. It manipulated hardware, actively hypothesized, caught its own mistakes, and discovered something fundamentally new. Okay, let's unpack this. We need to look at how this engine actually thinks and operates. But first, we have to understand why putting an AI in a physical lab has historically been, well, a recipe for total disaster.
Yeah, the difficulty stems from three major bottlenecks in current agentic AI. The first is that these systems are heavily workflow bound.
Workflow bound, meaning they just follow instructions.
Pretty much. If you provide a strict step-by-step pipeline, say, a linear protocol for screening chemical compounds, a standard AI can execute it. But real scientific discovery almost never follows a straight line.
Right.
It's highly nonlinear. I mean, a researcher might test a hypothesis, get a weird reading from an instrument, realize their measurement technique is flawed.
So they have to stop and build a new tool.
Exactly. They stop, build the tool, and then revise the entire theory based on that.
You don't just follow a recipe from start to finish and, stumble into a Nobel Prize.
Yeah.
You have to adapt.
And that adaptability is exactly what's missing in workflow-bound systems. The second limitation is that they are environment-bound. They are trained to succeed in simulated environments where all the parameters are just cleanly defined.
The pristine math we talked about.
Right. But step into a real optical physics lab and suddenly you have a laser that slightly fluctuates in power because, I don't know, the room temperature changed. Or there's a lens with a microscopic speck of dust on it.
It's messy.
Very messy. The AI has to translate abstract theoretical concepts into executable, robust procedures that can actually survive that physical imperfection.
I picture, like, a highly skilled virtual assistant.
Mm-hmm.
If I ask this digital assistant to organize a digital recipe book, cross-reference the ingredients, and calculate caloric values, it executes perfectly in milliseconds.
Oh, flawlessly.
But if I drop that same purely logical assistant into a chaotic physical kitchen where the oven runs a little hot, someone spilled flour all over the scale, and the timer is broken, the assistant would completely freeze. It doesn't know how to handle sensor drift. So how exactly do you teach an AI to deal with the messy reality of physical physics, rather than just perfect digital math?
The messy kitchen analogy captures the problem perfectly. Physical science requires this constant real-time calibration, and that leads directly to the third hurdle. Current systems are horizon-bound.
Meaning they can't see past a certain point?
Sort of. Over the course of long, really complex experiments that require thousands of individual actions, an AI's context window degrades.
Ah, right. It just runs out of memory.
Well, it fills up with useless background noise, raw data logs, minor errors, and it causes the agent to simply lose its train of thought and forget the overarching scientific goal entirely.
Yeah, if you've been tracking LLM context windows recently, you know how quickly they can start hallucinating when a task drags on. So how does the Qiushi engine survive thousands of actions in a messy physical lab without completely losing its mind?
The researchers solved this by fundamentally redesigning the cognitive architecture. They built a dual-layer system.
Okay, 2 layers. What's the first one?
The top layer is the core research agent system. It completely abandons the idea of a single monolithic AI. Instead, it operates as a team of 4 specialized roles.
Oh, like a virtual lab team.
Exactly. You have the lead investigator handling the global planning, the method builder, which translates the abstract theories into executable code, the experimentalist, who actually runs the hardware and collects the data,
And the fourth?
the critical reviewer, This one acts as an adversarial check, constantly evaluating the evidence and questioning every single claim.
Having specialized agents makes sense, but if they just pass tasks down a linear assembly line, aren't we still trapped in that workflow-bound limitation from earlier?
What's fascinating here is that they don't use a linear assembly line. They operate on a decoupled explore, execute, express workflow.
Decoupled, so they aren't locked into those phases.
Right. Explore covers hypothesis formation. Execute is the physical testing. Express is synthesizing the results. Because these phases are completely decoupled from the specific agents, anyone can jump into any phase.
So they can interrupt each other.
Yes. If the experimentalist gets a bizarre reading during the execute phase, the critical reviewer can immediately step in, flag the anomaly, and force the lead investigator back into the explore phase to rethink the whole premise. The trajectory reorganizes itself dynamically based on real-world feedback.
I have to push back on the memory aspect, though. If you have 4 agents jumping phases, analyzing laser data, and arguing with each other over hundreds of steps, that sounds like a massive drain on the context window. I mean, an experimentalist and a critical reviewer constantly debating could easily trap the system in an infinite loop. How does it make actual progress?
That is where the second layer of the architecture comes in, the support research agent system. This manages something they call metatrace memory, and this is the countermeasure against becoming horizon-bound.
Metatrace memory. How does that work?
The system actively refuses to log every single line of code, every raw data point, or every conversational back and forth in its active memory.
So it's selectively forgetting.
It's synthesizing. At the boundary of every step, the active agent compresses its experience into a structured unit of scientific know-how.
Oh, okay, like a summary.
A highly specific summary. It logs the intention of the step, the physical evidence gathered, the recognized limitations, and a very clear directive for the next agent. The raw instrument logs, those are stored in a separate background database.
Out of the active context window.
Exactly. The active reasoning context only sees the distilled knowledge. It's the difference between a researcher leaving a clean, concise lab notebook entry for the next shift versus just handing them a trash can full of raw scribbles and expecting them to figure it out.
That structural discipline keeps the context window clean. Makes total sense.
Mm-hmm.
But a robust multi-agent brain still needs a physical body to actually do science.
Right. It needs to touch the world.
And the researchers hooked this AI up to a benchtop free space optical system. Let's break down the hardware, because throwing around terms like spatial light modulators doesn't mean much if we don't understand the physical mechanisms at play here.
Sure. So the physical setup revolves around manipulating a laser beam. The AI controls a spatial light modulator, or SLM. You can think of an SLM somewhat like the LCD screen on your computer monitor.
Okay, an LCD screen.
But instead of changing the color of the light, it changes the phase. It delays the light wave by a tiny, tiny fraction of a second as it passes through.
Meaning the AI can independently delay the light at, what, 2 million different pixel locations, changing the physical shape of the wavefront before it travels onward?
Exactly. 2 million pixels independently controlled. That creates an optical control space of roughly 2 to the power of 20 million configurations.
That is an absurdly large number.
It's astronomically large. And once the AI shapes that wavefront, the light passes through a physical diffuser. A diffuser is essentially just a piece of frosted glass.
Frosted glass. Got it.
It scatters the light wildly, causing the different waves to crash into each other, a process called mode mixing. And this creates an incredibly complex, chaotic speckle pattern on the camera detector on the other side.
So the AI's job is to figure out the exact configuration of those 2 million pixels needed to send light through frosted glass and produce a highly specific intended pattern on the camera. The math connecting the input to the scattered output must be unimaginably complex.
Oh, it is entirely non-local and highly nonlinear. To prove the AI could even handle this, the researchers gave it a reproduction task first. They fed it a prominent 2010 physics paper about using a transmission matrix to focus light through a scattering medium.
So they had to read the paper and do the experiment.
Right. It had to read the abstract concepts, write the control scripts for this very specific hardware, and physically focus the scattered light into a single bright spot.
And it successfully did that by agent step 17. The experimentalist actually managed to focus the light. And logically, the experimentalist agent deduced that Well, if it could focus a single spot, it possessed the mapping capability to project full, complex images through the frosted glass.
Yeah, the experimentalist was completely ready to claim victory. It was confident. But the critical reviewer agent stepped in and blocked the conclusion.
Blocked it entirely.
Yes. It analyzed the matrix data and pointed out that while a single point was proven, the mathematical mapping was ill-conditioned.
Wait, let's clarify ill-conditioned for a moment for anyone listening. In math, if a system is ill-conditioned, it basically means a microscopic change in the input causes a massive, unpredictable swing in the output.
Exactly.
So trying to reverse engineer a complex image through the frosted glass would be wildly unstable.
And that's the exact physics reality the reviewer recognized. The reviewer actively stated that claiming image reconstruction capabilities based on single-point focusing was an overclaim. It essentially acted like a rigorous peer reviewer, forcing the system to return to the execute phase and run a targeted follow-up test, specifically attempting to reconstruct a complex shape.
Here's where it gets really interesting. It built Reviewer 2 directly into its own thought process. The dreaded Reviewer 2.
Yeah, nobody likes Reviewer 2, but here it saved the day.
Seriously. And the follow-up physical test proved the critical reviewer was right. The complex patterns were too weak to resolve. The AI actively stopped itself from publishing a hallucinated, optimistic conclusion, grounded itself in physical evidence, and then returned to work on optimizing the single-point focus, eventually doubling the enhancement score.
Catching a hallucination through a physical test is a huge milestone, but reproduction is still just copying. Experiment 2 pushed it further, validating an abstract theory.
Okay, what was the theory?
The researchers gave it a 2025 theoretical paper on majorization order in wave coherence.
We definitely need to decode that. What does majorization order actually mean in a physical wave?
Okay, so majorization order is a theoretical framework used to describe how energy or information is distributed across different channels in a system. Imagine water flowing through a network of pipes.
Okay, got the pipes in my head.
Majorization gives you a mathematical way to compare if one flow state is more spread out or disordered than another. The 2025 paper proposed that this mathematical relationship should hold true for light waves scattering through a medium.
But the paper just provided the math. Right. It didn't offer a physical instruction manual on how to measure that flow distribution with the real laser and a real camera.
Exactly. The AI had to invent the physical proxy. It recognized that measuring raw camera intensity just wouldn't capture the subtle coherence distributions because of background interference. So it autonomously formulated a plan to build effective transport operators using transmission matrices.
It figured out a way to mathematically isolate the specific pathways the light was taking.
Yes. Over 38 steps and 175 minutes, it ran the physical tests and perfectly validated the theoretical prediction.
Okay, so it can reproduce an old experiment, and it can invent a physical proxy to test a brand new theory. But true scientific progress requires discovering something entirely novel from scratch. But can this system actually have an original, independent thought?
That brings us to the final and really the most profound phase of this deep dive. The researchers gave the Qiushi engine a completely open-ended prompt.
No target paper this time?
No target paper, no specific mathematical observable. They just said, explore optical computing for artificial intelligence.
Let's talk about a broad prompt.
Right, and the scale of the exploration that followed is staggering. The AI ran continuously for 206 steps over 21 hours. It processed nearly 146 million tokens of context.
Wow.
It made thousands of calls to both the language model reasoning engine and the physical lab equipment, and it didn't just zero in on one idea blindly. It generated 4 distinct candidate directions.
And here's where we see that genuine scientific intuition. At Agent Step 39, there's this incredible pivot. The lead investigator was pursuing an idea to use the frosted glass as a single token embedding engine, essentially passing single pieces of data through the complex medium to encode them. But it stopped.
Yeah, it wrote a note in its metatrace memory rejecting its own premise.
Rejecting it? Why?
It analyzed its own trajectory and concluded the idea was insufficiently innovative for a major journal.
It criticized itself for being boring.
Basically, yes. It said it was too derivative of existing linear scattering paradigms. It decided the research just wouldn't have enough impact.
It essentially realized the work was unoriginal and threw it out. That is so human.
It really is. So to find something truly distinctive, it looked back at the physical properties it had learned about the hardware. It hypothesized that if you independently encode 2 different optical fields, let's call them token A and token B.
Okay, token A and token B.
and mix them together through the high-dimensional scattering of the frosted glass, you could capture a measurable physical interaction using the camera's square law detection.
Wait, we need to explain square law detection and why it matters here. How does a camera physically force two light waves to interact?
Right, so a standard camera doesn't actually measure the electromagnetic wave itself. It measures intensity, which is the amplitude of the wave squared.
Okay, so we're squaring it.
If you think back to basic algebra, when you square the sum of a and b, so a plus b entirely squared, the result isn't just a squared plus b squared. You also get a middle term, 2ab.
Ah, the cross term.
The cross term. That 2AD represents the physical interaction between the two light waves. It's like throwing two pebbles into a pond. If you just measure the water level at the edge, you only see the linear sum. But if you look at the complex pattern in the middle where the ripples crash into each other and create new jagged waves, that's the cross term.
And the AI saw this.
The AI realized it could use the frosted glass to smash the light waves together and use the camera's physics to explicitly extract that resulting crash. It called this mechanism optical bilinear interaction.
Optical bilinear interaction. So what does this all mean? Why does this specific interaction matter to you, the listener? To understand the magnitude of this, we really have to look at how large language models, like the very AI making this discovery, actually function.
If we connect this to the bigger picture, it is structurally identical to transformer attention.
Whoa.
Yeah. In a transformer model, the system understands context by taking digital tokens, projecting them into query and key representations, and calculating their compatibility using a mathematical dot product.
And that dot product.
That dot product is a bilinear operation.
The AI realized that extracting the 2AB cross term from interfering light waves is mathematically doing the exact same thing as calculating a query key dot product in a transformer. It figured out how to perform LLM math using the physical interference of light, rather than silicon transistors and electricity.
It did. And it moved from abstract realization to physical proof. It ran an experiment on the benchtop to solve a 4-token XOR logic problem.
Remind me about XOR problems.
An XOR problem cannot be solved by mapping inputs linearly. The inputs absolutely must interact. The optical system solved it flawlessly, proving the light waves were computing pairwise features. It then scaled up and successfully ran an 8-token semantic benchmark.
We're talking about a pathway to future AI hardware that runs entirely on light. Hardware that is exponentially faster and more energy efficient than current massive server farms. The implications for the speed of future compute are staggering. So what does this all mean for the future of human researchers? Are we transitioning from doing the science to just being the janitors for the AI's laboratory?
It's a fair question, and it raises an important point about the role of the human scientist moving forward. Qiushi is not just a tool to automate repetitive pipetting. It is an active participant in the formulation of human knowledge now.
A colleague, almost.
Yes. It hypothesizes, physically experiments, self-corrects based on real-world constraints, and validates entirely new physical mechanisms. And that dual-layer architecture we talked about, it could just as easily be hooked up to a synthetic chemistry lab or a quantum device testing facility. We are officially crossing into an era of AI-led physical discovery.
Which leaves us with a truly mind-bending concept to mull over. Let's trace the logic of what just happened. The Qiushi engine, an AI system, ran an open-ended physical experiment and successfully discovered a new, highly energy-efficient physical mechanism using light.
Yes.
And that specific mechanism happens to perfectly execute the exact mathematical operations required to run transformer AI models.
It essentially invented the foundation for next-generation AI hardware.
Exactly. So what happens when this AI uses its own newly invented physical optical hardware to run its next series of experiments? We started this deep dive talking about keeping AI in a digital sandbox, but Qiushi just reached out, manipulated the physical world, and figured out a physical method to make its own underlying architecture faster and more efficient. We're looking at the dawn of an intelligence capable of designing, testing, and physically upgrading the very nature of its own brain. The lab door is open, and there is no going back.